As a capacitor discharges, how does the voltage across it and the current flowing through the circuit change over time? In this video, we'll find out using the PASCO wireless voltage current sensor. PASCO's wireless voltage current sensor is a smart alternative to a traditional multimeter. It can be used alone with its built-in display for quick readings, or connected to a computer or other device to record and graph data. It measures both AC and DC voltage and current, and because it can measure voltage and current simultaneously, it can also measure power and energy. It includes 4 alligator cables and a USB cable. I've built this circuit containing a battery, a capacitor, and a resistor. I'm using modular circuits components, but you can also use any battery, capacitor, and resistor that you happen to have. I've connected cables to the sensor's current ports so that it completes the circuit and current can flow through it. When the switch is in this position, the battery is included in the circuit and current flows around the circuit like this. And when the switch is in this position, the battery is bypassed and current flows around the circuit like this. I'll return the switch to the charging position. I've also connected the sensor's voltage ports across the capacitor to measure voltage. Even before I connect the sensor to the computer, we can see the voltage is about 1.5 volts, and current is close to 0. When I flip the switch, we see that voltage starts to decrease and the current is negative, indicating that current is flowing in this direction. And when I flip the switch this way, the voltage increases and the current is positive. I'll return the switch to the discharge position. We can also record and view these measurements on a computer. I'm using SPARKvue, but you can also use Capstone software. I've already connected the sensor to the computer through Bluetooth and set up a graph to display voltage versus time. Let's start data recording and see how the voltage changes when I flip the switch. You can see the capacitor charging up to the same voltage as the battery, and when I flip the switch the other way, it discharges. I'll return the switch to the charging position and stop data recording. Let's suppose we want to find the curve fit for this part of the data, where the capacitor is discharging through the resistor. It will be easier if we only see the discharging data, so I'll delete this run. And now collect another run of data, starting after I flip the switch to the discharging position. In theory, we would expect this to be an exponential decay, and we can select a natural exponent fit to show that it is. We didn't just measure voltage, we also collected current data, which I can add to the graph. And we can add another curve fit to show that this is also an exponential curve. In this circuit, as the capacitor discharged, it delivered power to the other components of the circuit, mainly the resistor. On a new page, let's look at a graph of power. It's negative, showing that power is flowing out of the capacitor, and it gets smaller over time as the voltage and current decreased. If we're curious about the total energy dissipated by the circuit over time, we can find the area between the curve and the axis. which in this case is about negative 0.1 watt-seconds. Again, it's a negative value because energy flowed out of the capacitor. Or we can graph energy versus time and find the change in energy stored in the capacitor. And we find the total change in energy was the same value, negative 0.1 joules. Visit the product page linked in the description to learn more about the wireless voltage current sensor and its accessories, including specifications and links to lab investigations. Thanks for watching.